Hello and welcome. My name is Jacqueline Liebman, Project Manager for Team 13, and it is my honor to present this preliminary design review as part of the Space Mission Concept Academy, along with the other members of the Enceladus 7 team. Today we will be presenting our design concepts and scientific objectives for the Ptolemy 1 mission lander to Saturn's moon, Enceladus. And now the Enceladus 7 team will introduce themselves. Again, my name is Jacqueline Liebman, Project Manager and Outreach Co-Director, and I graduated from the University of North Carolina at Chapel Hill in 2019, and I currently attend Fayetteville State University. John V. Kateria is our Deputy Project Manager, and she attends the University of Alabama.
My name is Sarah Kaiser. I am Science Lead and Outreach Co-Director. My major is Biochemistry, and I go to Arizona State University. I currently reside in Winston-Salem, North Carolina.
Hi, I'm Alexis Warren. I'm a sophomore mechanical engineering major at Tidewater Community College. I live in Norfolk, Virginia, and I'm also the engineering lead for the mission.
Hi everyone, my name is John Duton. I am a third-year computer engineering major at the University of Maryland. I currently reside in Hanover, Maryland.
Hi, I'm Mohammed Mubashir Sheikh. I'm the aerospace and robotics lead, and I'm currently an aerospace engineering major at the University of Maryland College Park, and I reside in Silver Spring, Maryland.
My name is Fatima Karoma. I go to the University of Pennsylvania, and I serve as the safety deputy and financial planner for Team 13.
The Ptolemy 1 mission is comprised of an orbiter and a scientific lander, Ptolemy 1, which is inspired by Ptolemy II Philadelphus, pharaoh of Ptolemaic Egypt, who was ruler at the time of the Library of Alexandria's construction. Now, centuries later, Ptolemy is returning to Alexandria, but instead of Egypt, the actual location will be the Alexandria Sulcus, which is part of the Tiger Stripe region of Enceladus. Ptolemy's main objectives are to collect topographic and environmental data, along with chemical analyses in order to provide future missions with better knowledge of the surface and internal composition of Enceladus. While there is their belief that one day we might find life on Enceladus, the goal of our smaller and shorter mission is to collect vital data necessary for researchers to formulate hypotheses to be possibly investigated by bigger missions.
So this is our mission concept and success criteria. First of all, we plan to safely approach Enceladus and deploy the secondary payload from the orbiter. Second of all, while in descent, the MLA is going to conduct altimeter readings of up to 8 points per second, scanning the surface using the laser, and then once it's done scanning, we're going to suspend the power supply to the instrument. The maximum height this is going to occur at is 382.8 kilometers as the orbit's elliptical. The height isn't the same. Isn't going to stay the same as it's conducting the scans. Third of all, the lander is going to descend to the surface and arrive within the Alexandria Sulcus landing site at a latitude of -71.938 degrees north and longitude of 199.812 degrees east, with a minimal amount of risk to the payload. Next, power is going to be initiated to all surface level instruments. Then Sherlock is going to perform a calibration test using the Watson calibration target in order to get accurate and precise measurements on the surface. Then Sherlock, REMS, and the ZChem V1 Pro are going to register a charge. The seventh point on the success criteria list is that at least 5 surface images are going to be collected using Sherlock Watson and the ZChem. Finally, the lander is going to maintain functionality for the entirety of the 1-month mission. Other requirements for the mission are that the volume has to be contained within a 51 centimeter by 51 centimeter by 76 centimeter box, which our mission does. It fits exactly those requirements. And the weight has to be less than 77 kilograms, and our weight rounded out to 76.2 kilograms, so very close. On the left is a CAD model of the lander. I will talk about that in a minute and explain it further.
One's mission objectives were inspired by the first Mars missions and the proposed Europa Clipper mission. In Objective 1, we'll be investigating the topographic and geomorphic features in the Tiger Stripes region. In Objective 2, we'll be assessing the internal structure and chemistry of plume debris found near our landing location. And last but not least, we'll be investigating 6 atmospheric parameters: wind speed, direction, pressure, relative humidity, air temperature, ground temperature, and ultraviolet radiation using REMS.
Our mission schedule is as followed. Phase 1 began October 1st of 2020, and our projected mission closeout will be in March of 2030. Our science team has spent several months developing their mission goals and objectives. Once they were established, we entered Phase B and began to develop our technical plan as well as determine our manufacturing and testing facilities. We are at the end of Phase B with this preliminary design review. Phase C will begin with the submission of the finalized and edited document. After the submission is approved, design and development of the lander will begin in October of 2022 and will take until the rover assembly integration in April 2025. The majority of testing, or Phase D, will take approximately 15 months to ensure the lander components will operate safely and effectively on Enceladus. The operations phase kicks off with the much anticipated launch in February of 2027. Launch to the arrival of Ptolemy 1 to Enceladus will take approximately 3 years to complete. Once Ptolemy 1 is deployed from the orbiter, the first step is to initiate power supply to the MLA for at least 24 hours before it can be used. In hour 26, the lander will begin its descent to the surface and MLA will enter science mode to begin scanning the Tiger Plume area. Upon safely landing, Ptolemy 1 systems will be checked and then the surface level data collection portion of the mission will begin. Ptolemy 1 will have 1 month to collect data before power and communication to the orbiter are cut off and the lander is abandoned on the surface. The communication orbiter will then be sent on a collision course with Saturn. Project closeout is expected March 27th, 2030.
Here we have Ptolemy 1's scientific instrumentation. First, we have MLA, which will be used to take an image of the Tiger Stripe region in descent. Secondly, we have REMS, which will give us data on the atmospheric condition of Enceladus' surface. Next, we have Sherlock accompanied by Watson, which will analyze the plume fallout in our landing location. Last but not least, we have ZCAM V1 Pro, which will be used to take 3D images at the perspective of the lander in 360 degrees. That completes our science payload.
So this is our N-squared chart that explains the relationship between the 6 subsystems on our lander. The 6 subsystems are the instrument data gathering subsystem, the power subsystem, the data storage subsystem, the communication subsystem, the thermal subsystem, and the computer subsystem. First of all, the instruments are going to collect data and transmit that raw data to the data storage, which is just an SSD memory storage bank. The reason this SSD memory storage bank is on board is because SSD memory actually consumes less power than normal computer flash RAM memory, which means the lander can conserve energy by using this SSD data bank. The data bank will then transmit that raw data to the computer, which will store it as backup in case something happens to the SSD data bank. The power system is comprised of a lithiated cobalt nickel aluminum oxide battery, which will send 130 watts of power to the instruments, 62.85 watts of power to the SSD storage bank, 10 watts of power to the antenna, and 3.5 watts 10 watts of power to the radio, and 3.5 watts of power to the antenna, which make up the communications package, 70.5 watts of power per heating pad, and 14 watts of power to the computer. Our thermal system is made up of heating pads produced by Minko, and they will continuously warm the instruments, the battery, the SSD bank, the communications package, the radio, and the computer. Additionally, there will be a thermal sensor in the electronic spots that monitors the temperature of the battery. Since we want to prevent the battery from overheating, that's super critical. And it will send that thermal sensor data to the computer, which can shut off the heating pads if the lander overheats to prevent malfunctioning. The computer, in turn, is going to enact autonomous procedures on the instrument's power, communications, and thermal systems in case anything malfunctions, especially for redundancy purposes. The computer also acts as a data backup to the SSD RAM banks, as I said earlier. And this is our lander design with a nice CAD model. So first of all, it's comprised of an electronics box that is made up of 2 of the lithiated cobalt nickel aluminum oxide batteries I talked about earlier, a voltage board which steps up the battery's nominal voltage of 3.6 volts to 28 volts, which is what the MLA and Sherlock and Watson need to function correctly. It's also comprised of a thermal sensor which will send data to the computer, which can shut off the thermal system in case the lander overheats, since we want to protect the battery from overheating. The next component is the SSD memory bank on board. It's the spots right here. It can store up to 23 terabytes of data, which is a lot. No, it's a really large amount for a lander. It should meet all of the requirements the instruments need. So the instruments send the data directly to that SSD memory bank for storage. And in case that SSD memory bank malfunctions, the computer would be the backup for that, since there wasn't enough space on board for another SSD bank. So heat sinks are next. They make up the thermal system. Their main purpose is to distribute heat away from the computer so they don't overheat. But they can also function to distribute heat away from the lander in case the lander overheats. So RAD 750 SITU computers make up the computer system. There will be 2 on board for redundancy purposes. They control all the autonomous procedures on board, and they will also contain a pre-programmed flight path for the lander and thrusters to follow in order to land in the right place. Speaking of EDL procedures, we also have a gyroscope and an accelerometer on board, which function to take measurements during EDL. So the gyroscope takes angular measurements, which will help stabilize the rover during EDL, and the accelerometer takes speed and acceleration measurements, which will help the lander know when to land when the speed is under a certain amount. Next up are the heating pads, which are the main thermal component for a thermal system. They're produced by Minco. Each heating pad produces 70.5 watts of heat. There are 4 on board for redundancy purposes. However, I don't expect all 4 to be running at once. 2 will be running maximum at night, but during the day, I expect only 1 will be needed. The rest are there in case the rover malfunctions, or in case thermal estimates are vastly underestimated. Next up is the communications package, which consists of 2 radios and an antenna. This will provide communication to the rover and will allow the rover to send data directly back to Earth. The MLA also has a separate transmitter receiver component to it, which can function as a backup communications device in case the main communications package malfunctions or fails or gets damaged upon EDL. Next up are the thrusters. They're monopropellant hydrogen thrusters, which use liquid hydrogen as fuel. There are 4 on board, and each thruster provides 1 newton of force. The required force we need for EDL is actually 3.5. So there's not a lot of room for error. However, if one of them malfunctioned as it was close to Earth, the lander could probably still land safely. And then next up are the instruments. The MLA is on the bottom, and there's a hole cut out on the bottom and will be filled with sapphire in order for the MLA to take laser measurements of the surface. The Zcam and RAMs will be connected through a mast, which will have the ability to raise above the top of the lander once the lander lands on the surface. The panel on the top will be a sliding glass panel, which will slide out of the way to let the mast raise. Last of all, Sherlock and Watson are going to be latched to the bottom of the lander and connected to the side via a robotic arm, which will move it up under the bottom to the side to allow it to take measurements. once it lands on the surface. On all, the volume constraint was 51 centimeters by 51 centimeters by 76 centimeters, and it fits that exactly. The mass constraint was 77 kilograms, and the lander weighs on at 76.2 kilograms.
Entry, descent, and landing. The descent maneuver employs a Hohmann transfer in which, at an altitude of about 196.8 kilometers, the Ptolemy 1 fires its thrusters for the first time, this time in the retrograde direction or backwards, in order to create a change in velocity of around 20.8 meters per second and enter a lower orbit that eventually guides the lander towards its designated landing zone within the Alexandria Tiger Stripe region. A few moments later, at an altitude of around 203 kilometers, the Ptolemy 1 fires its thrusters for a second time, this time in the prograde or forwards direction, again aiding in its transfer into a lower elliptical orbit. The final maneuver occurs as the lander enters Enceladus's atmosphere. The thrusters fire for the third and final time, perpendicular to the moon's surface. This is done in order to eliminate the lander's entry velocity from 209.7 meters per second to 0 meters per second for a safe landing on Enceladus's icy surface. As you can see from these images here, the pink first represents the orbiters and initial orbit around Enceladus, while the green represents the Ptolemy 1's trajectory after its third thruster burn. And here you can also see the blue-ish parts, valleys here on this graphic represent the Tiger Stripe region that we're interested in. And what's hard to see is here where the Ptolemy 1 actually lands in the Alexandria landing zone. So the Hohmann transfer takes a total of 4.1475 hours to complete and requires a thrust of 1.2 newtons. The four 1 Newton monopropellant hydrazine thrusters aboard the Ptolemy 1 more than account for the amount of fuel required to complete this transfer, and also the single burn life of 12 hours more than accounts for the thrust required to complete the descent maneuver. So from this graphic here, which shows the EDO sequence from Enceladus's surface point of view, you can see that the Ptolemy 1 is first entering its final Hohmann transfer orbit, and second here, you're going to see the Ptolemy 1 begin to ignite its thrusters for the third time to decelerate from around 209 meters per second to 0. And here we see it's vertically upright and keeps descending towards Enceladus's surface at a slower rate. And fourth and final, we see the Ptolemy 1 has landed safely on Enceladus's surface and is ready to conduct its science missions. So this is my free flyer simulation on the Ptolemy 1's entry, descent, and landing sequence. The pink is again your initial orbiter's orbit. The second green line here is after our second thruster burn, and this view will show you a better view of where we're actually landing Ptolemy 1. This yellow box is our Alexandria landing zone that we would like Ptolemy 1 to land in.
This slide shows our landing site. Our landing site is located in a wide area between two plumes that are opposing each other. We chose this because our lander will still be safe, but it'll be right there in the action, so it can analyze plume debris.
All right, for our failure mode effect analysis, we decided to observe our 3 mission objectives. The first being investigating topographic and geometric features in the Tiger Stripes region, including the landing zone that we're going to be at, assessing the internal structure and chemistry of Enceladus through chemical and mineralogical evaluations of surface debris created by the plume fallout, and finally investigating the 6 atmospheric parameters we keep track of before, during, and after the mission, be it wind speed, direction, pressure, relative humidity, air temperature, ground temperature, and ultraviolet radiation. We identified several ratings for each of these objectives, including severity rating, the estimated number of occurrences these risks will occur, determined level rating, and the risk priority number. Alongside, we identify cause and effect that would allow these risks to come into fruition, be it because of improper calculations given by the instruments, or improper mechanical features or implementation of the instruments within the lander. And finally, improper predictions and analysis by our team before, during, and after the mission. And each one of these risks pretty much influences the other risks, For example, should we get improper, inaccurate, or misleading information about surface atmospheric conditions, that would affect their landing. Ergo, the first function would affect the third function, and our landing would be jeopardized. More so, our landing could be jeopardized for proper execution once it lands on the surface of Enceladus. These recommended actions are pretty much self-explanatory. So long as we provide careful analysis of each instrument that we'll be using, know exactly how to use them and how to fix them should anything go wrong, we believe that we can clearly identify a great discrepancy throughout the mission.
Today I'm going to be talking about the failure mode and effect analysis for the engineering payload, specifically the communication system. One of the functions of our communication system is allowing communication between the team and the rover. A potential failure mode is the signal being blocked by the lander being at an angle where it faces away from the Earth. If the team loses communication with the rover, we can't communicate and see how the rover is doing. A potential prevention is a backup autonomous program that doesn't depend on the instrument ion. However, this isn't a permanent solution. My recommendation to alleviate this risk is to implement an autonomous program that allows the rover to land without communication from the team. Since our communication system is powered by a battery, another risk is that the battery dies. If the battery dies, there will be no way for the team to communicate with the rover. This can occur one of two ways: if the battery becomes dislodged, or if the battery simply dies because more power is expended than we expected. A prevention that we have in place is auxiliary power from the CPU and RAM. However, this would only last 50 minutes. My recommendation to alleviate this risk is to have a backup power generator that will automatically kick in if something happens to our battery. Our spectrometer is responsible for analyzing atoms in a sample. An issue that can occur with this is reflectivity of the surface affecting our spectrometer's readings. In terms of design control, we have a relatively protected spectrometer. However, this can still allow for reflectivity of the surface. This would cause inaccurate data compared to measurements of standard atoms. My recommendation to alleviate this worry is to have expected data from different atoms out and ready to compare, so we know if our spectrometer is giving us inaccurate readings. Another failure mode is the antenna being affected and not allowing us to have clear communication with the rover. We're going to be able to tell if this is occurring if the signal is impaired and becomes increasingly weak. Our antenna is designed with a strong support system that does not affect the signal of the antenna. This is the only recommendation I have to alleviate this risk. Blockage and our battery dying are ranked as our two most severe failure modes, as if these occur, we will not be able to communicate or use our rover. While signal blockage would give us a warning sign of an increasingly impaired signal, it would still be hard to detect and prevent. Our two highest failure modes are battery dying and there being reflectivity on the surface affecting our spectrometer. We have systems to prevent both from occurring. Overall, our highest risk based on our FEMA is the spectrometer picking up reflectivity of the surface. And this is so high is because it's fairly likely to occur, and if it does occur, it is hard to prevent to prevent us from collecting accurate data with our rover.
This budget showcases our whole mission, financial costs. As you can see here, we are comfortably under budget at approximately 346 million. Divided it up by three teams: science, the engineering team, and our administration team, which is pretty much factored into our salaries. The only administrative cost, which I'll explain later, is pretty much our outreach. But looking at this on a broad scale, we identify costs that we won't necessarily need to cover every year. For example, manufacturing and test facility costs until about the second year. Likewise, we decided to bundle all of the costs up into 1 year, given the fact that all of our contracts would be done within the first or second year. That is why we placed the total materials and supply within year one, anticipating that all the contracts and financial settlements will be done by that time, and that they will last throughout the entire mission. This is more of a breakdown of the budget. As you can tell here, the largest budget that we have for our entire mission is the engineering team's budget. This includes every single little part that goes into the lander and that holds all the instruments that the science team has. The most costly of these parts is the EDL capsule, which it's a given fixed cost because it's the only way that our lander can go up into space. Even though we lose it within entry and descent into Enceladus. Nevertheless, we wanted to make sure that our lander makes a proper descent onto the Saturn moon. For our science team, we identified several key instruments that although not necessarily on the conservatively cheap side. We feel will give us the most accurate information, let alone gives us many fail safes should they perform badly.
Our goals for the outreach department were based on two approaches: virtual engagement and K 12 outreach. Our social media team plans to create a mission website, Facebook, Instagram, and Twitter, to allow users who follow on any platform the ability to watch the Enceladus mission evolve over its 10-year course. A fascinating feature of the mission website will be to add weather widgets based off of live data collected by REMS once it has landed on the surface. Now everyone who goes to the website can view the Enceladus weather forecast of the day. A large part of Facebook and Instagram will be to host NASA social events, where members of the group can interact and share their excitement for the launch. Our team will utilize the pre-existing NASA YouTube page to share the live launch coverage out of Kennedy Space Center for users around the world. Our K 12 outreach involves creating educational material about Enceladus and the Ptolemy 1 mission and have it published to the NASA STEM engagement website. Currently, there are plans to upload possible class project templates, such as making a model of Enceladus out of a styrofoam ball or other materials, having students design their own subsurface Enceladus world, and how to make a 3D model of Ptolemy 1. There will also be an Enceladus drawing competition entitled The Future is Bright, whose title plays off of Enceladus' surface being highly reflective. Students in grades 3 through 5, 6 through 8, and 9 through 12 will create their own logo design representing the capabilities of STEM students and their impact on the future of space exploration. The top designs from each category will win a $1,000 college scholarship, and their logos will be added to the Ptolemy 1 lander, while the second and third place winners will receive a $500 college scholarship each. The first place students will also be invited with VIP access to launch day at Kennedy Space Center in Florida. Being as 60% of NASA scientists are reaching retirement age, it is vital to engage students in STEM education as early as possible and continue to cultivate their passion for STEM and emphasize the importance of STEM career options. Ptolemy 1's mission will take approximately 10 years to complete from start to finish. Our team had to overcome numerous challenges while working on this project. Aside from given mission constraints, our team worked 100% virtually and was able to overcome setbacks, such as working through the COVID-19 pandemic and losing numerous team members along the way. Despite everything, the Enceladus 7 managed to create a lander that we project is suitable for use on Enceladus. We hope that you are as excited as my team is to bring Ptolemy back home to Alexandria. Thank you.